Guys, good morning to all. Good afternoon. So, this is the first class. Yesterday, you were. So, right, guys, till where we have done yesterday? Till where? What is the topic?
Sir, we had started calorimetry.
Yeah, calorimetry started. In the calorimetry, what was done? What was done, guys, in calorimetry?
Sir, heat capacity or thermal capacity?
Heat capacity is thermal capacity completed. So next, specific heat. Okay, so yesterday once go through that. Yesterday what we have given thermal capacity means heat required to raise the entire mass of the substance by 1 degree Kelvin or 1 degree centigrade. That is known as specific heat. For example, what we have taken, we have taken a block of mass m. Let the amount of the heat is supplied to this block of mass, so that we notice that there is a heat rising temperature. Then the heat capacity means thermal capacity means to get the theta rise of temperature, we have supplied the amount of the heat. Then to get 1 degree rise of temperature, we have to get a heat of dq upon dt. So this is the heat required or heat supplied to this block of mass to raise its temperature by 1 degree Kelvin or 1 degree Celsius. That is known as heat capacity or thermal capacity. So then what is mean by specific heat means so simple instead of considering this entire block, if I consider a unit mass, the heat required to raise a unit mass of substance to 1 degree Kelvin or 1 degree centigrade. The amount of heat that must be supplied to a unit mass of substance to raise its temperature by 1 degree Kelvin or 1 degree Celsius, that is known as the specific heat. The same thing we have taken. So for entire block means for m mass of substance to raise its temperature by 1 degree, we have to supply a heat of dq upon d theta means for m mass. Okay, for m mass to raise the temperature 1 degree, we have to supply a heat of dq upon d theta. Then for unit mass means for unit mass either it might be in CJ system 1 gram, in SI system it is 1 kg. For unit mass, what is the heat required? 1 by m of dq upon d theta. This is the heat required to raise the unit mass of substance to 1 degree centigrade or 1 degree Kelvin. The amount of the heat that must be supplied to the unit mass to raise its temperature by 1 degree Kelvin or 1 degree Celsius, that is known as the specific heat. What is an SI unit of specific heat means SI unit of specific heat. According to formula, here numerator stands for dq energy SI unit is joule. But in denominator, mass is there, temperature is there. Mass SI unit is kg and temperature SI unit is Kelvin. Joule per kg Kelvin is the SI unit of specific heat, and it can also be measured in. It can also be in. It can also be in calorie per kg Kelvin or you can calorie per gram centigrade. So this is about the SI unit. For example, specific heat of water is 1 calorie per gram centigrade. Or else we can write this value in terms of SI unit is 4200 joule per kg Kelvin. What it means that 1 calorie of heat is required for what? To raise 1 gram of water temperature by 1 degree centigrade or 1 degree Kelvin. Or in the same case, we can speak about 4200 joules of energy is required for what? To raise the 1 kg 1 kg water temperature by 1 Kelvin. So to raise the water 1 kg, what there is a 1 kg water is there. To raise its temperature by 1 Kelvin, we have to give the heat to that 1 kg water is 4200 joules. 4200 joules. Or else if there is a 1 gram of water is there, to raise this 1 gram of water temperature by 1 degree, one has to supply a heat of 1 calorie. That is meaning of that specific heat. Remember that the specific heat is more means that substance will be heated up slowly. If the specific heat is less means that substance will be heated very fast. For example, there is ocean surfaces are there, land surface are there. Which one of them will be heated faster? Either the surface of ocean or surface of the land, right?
Ocean, sir.
Ocean, not surface of the land. Why? Because means the specific heat of the clay mill is less than the specific heat of water. That's why that land surface will be heated very fastly when compared to the water surface. The reason is that specific heat of water is more than the specific heat of the land surface. Similarly, which one of them will be cooled down fast, either the water surface or land surfaces? Surface of ocean or surface of land? Land only. Why? Because means if the specific heat is more means, remember guys, that substance is heated slowly and cooled down slowly. If the specific heat is less means that substance will be heated rapidly and cooled down rapidly. That is the reason seawater will be heated slowly and cooled down slowly, but land surfaces will be heated fastly and cooled down slowly. That is the reason. Okay. So that is about the specific heat. First note down that specific heat. Okay. Then we'll go for water equivalents then. Note down this statement. The heat required for unit mass of substance, the heat required for a unit mass of substance to raise its temperature by 1 degree centigrade or 1 degree Kelvin. The heat required, specific heat means that is a readings. The heat required to raise the temperature of unit mass of substance through 1 degree centigrade or 1 degree Kelvin. Okay, that is called specific heat. You can write this formula. S is equals to 1 by m of dq upon d theta. SI unit is joule per kg Kelvin. It can also be means what is it stands for here? Unit. Unit stands for our specific heat can also be in calorie per kg Kelvin or calorie per gram centigrade. We can easily convert from one to another by knowing the 1 kg equal how many grams and 1 calorie equal how many joules. By knowing those values, we can easily convert from one unit to another and vice versa. Okay. So next one note you can write. Completed students.
Yes, sir.
Okay, Nama. So next note you can write. Specific heat of water. Specific heat of water is equals to 1 calorie per gram centigrade or that is equals to 4200 joule per kg Kelvin. 4200 joule per kg Kelvin. Okay, kg Kelvin. So make one note of this point. Okay, make one note of this point. So see here, S is equals to 1 by m of dq by d theta. So that implies dq is equals to what can I write? Ms d theta. what is this dq equal ms d theta means? So then if I write further, I can write here d theta is the temperature difference. That implies dq that's equals to ms of theta 2 minus theta 1. What it means that to increase the temperature of m mass of substance whose specific heat is S from theta 1 to theta 2, what is the heat required means that's equals to ms of theta 2 minus theta 1. Okay. The heat required to raise the temperature of m mass of substance whose specific heat is S from the temperature theta 1 to theta 2. For example, this is taken in glass. Okay. So this is initially whose mass is m, specific heat is S, temperature is theta 1. I am supplying some amount of the heat to this system so that there will be no change in specific heat and mass m and S, but here temperature is theta. So what the heat I need to supply to change the thermal condition of the system from here to here. So what is the heat I need to supply means the heat supplied is Q is equals to product of mass and specific heat and temperature difference theta 2 minus theta 1. So that is meaning of this formula. So that is about the heat required to raise the temperature from one value to another value, that's equals to ms into theta 2 minus theta 1. Okay. So till here just write this one dq that's equals to ms d theta, dq that's equals to ms d theta, ms d theta. Okay. So for variable specific heat, okay, variable specific heat. So then dq, okay, variable specific heat, heat supplied, Q is equals to integral dq, that implies Q is equals to integral theta 1 to theta 2 ms into d theta. So for example, if the specific heat is variable with the temperature, on such case how to calculate the heat supply means integral. I think you know this mathematical function integration and differentiation. So in case of variable specific heat, constant specific heat means directly we can use this relation dq that's equals to ms d theta, that's equals to ms of theta 2 minus theta 1. Heat required to raise the substance temperature from theta 2 to theta 1 is ms theta 2 minus theta 1. So where the specific heat is constant, if the specific heat is variable, then this is the relation. Integration techniques are used to identify the heat supplied or heat required to raise the temperature. So this is one of the. So for advanced questions we will get it mains level and NEET level. We won't get the questions on this. Advanced level we will get this type of questions. Variable specific heat. Okay, let us solve one or two problems based on this. Then you get better. Okay. So is it clear, guys?
Clear, sir.
Okay, so wait, next copy this. Next, copy it. Over. So next one is a relation between H and S. What is H stands for heat capacity? S stands for what? Specific heat. So we know that yesterday we have derived H is equals to what can I write? dq upon d theta, and specific heat S is equals to 1 by m of dq upon d theta. So then from this relation what can I write? S is equals to 1 by m of, in place of dq upon d theta means I can substitute the h value as equals to h. So that implies h is equals to m into s. So it means that so this is not only the formula to calculate the heat capacity, this can also be used. Heat capacity is nothing but the ratio of heat supplied to the rising temperature, that is known as the heat capacity of the body. Or else heat capacity is nothing but the product of mass and specific heat of the substance is also gives the physical quantity heat capacity. Which H equals to M into S. Depending upon the situation, we may able to use this relation or we may able to use this relation depending upon the situation. If you know about heat supplied rising temperature, then you are allowed to use this formula to get the value of H. Instead of heat supplied and rising temperature, sometimes the values are measured or mentioned with mass and specific heats. The non-such case, how to calculate the specific heat means the specific heat capacity is nothing but product of mass of the body and the specific heat of the. So this one. Next one of the important one, water equivalent. Okay, water equivalent. So let us see water equivalent. So so first let me write the definition of the water equivalent. Okay, then we can go to this. So the mass of water whose thermal capacity is okay equal to the thermal capacity of given object. Okay. So water equivalent is the mass of water whose thermal capacity is equal to thermal capacity of the given object. For example, let M is mass and S is specific heat. S is specific heat. So then the thermal capacity of an object is what? So then thermal or heat capacity both are same. So therefore heat capacity of body, heat capacity of the body, H is equals to heat capacity means in terms of mass and specific heat means product of the M and S. So let MW is mass of water. Okay, mass of water. So then, what is the heat capacity of water? Then, so therefore, heat capacity of water. Heat capacity of water HW that is equals to mass of water into specific heat of water. According to the statement, what is that? The mass of water whose thermal capacity or heat capacity is equal to the thermal capacity of given object. That particular mass of water is known as the water equivalent. So therefore, let MW is the mass of water whose thermal capacity is this one. That is equals to thermal capacity of the given body means. So therefore, thermal capacity of water that is equals to thermal capacity of the given object. Then mass of water into specific heat of water that is equals to M and S. So that implies mass of water that is equals to M and S divided by specific heat of water. So this is the mass of water whose thermal capacity is equal to thermal capacity of the given object. That's why this mass of water is known as water equivalent. So therefore, the water equivalent, okay, water equivalent, water equivalent is equals to M into S divided by specific heat of water. So this is meaning of that. Water equivalent. So just have a look on it. So what is mean by water equivalent means the mass of water whose thermal capacity is equal to the thermal capacity of the given object. That mass of water is known as water equivalent. So let we have taken a substance of mass m and a specific heat s. Then what is the thermal capacity of the given object? H is equals to product of mass and specific heat m into s. Let it. And let mw is the mass of water. This is the mass of water whose thermal capacity is equal to thermal capacity of the given body. So then if mw is the mass of water means what is the thermal capacity of the water? Thermal capacity of the water is nothing but similarly product of mass of water and specific heat of water. According to this, the mass of water whose thermal capacity is equal to thermal capacity of the given object. So if I equate the thermal capacity of water and thermal capacity of the given object, then I got this is the mass of water whose thermal capacity is equal to thermal capacity of the given object. So then this mass of water is known as water equivalent. Hence water equivalent that is equals to ms by specific heat of water. So why water equivalent will be given means instead of giving the data directly, water equivalent is given means specific heat of water is a standard value. We can know about the thermal capacity of the given object. Instead of giving mass and specific heat, sometimes they may give water equivalent. So by using water equivalent, we can calculate the heat capacity or product of m and s can be calculated by knowing this specific heat of water is a standard. It is 1 calorie per gram centigrade. So that is the reason why water equivalent will be given means. So got it, students? Water equivalent, is it clear?
Sir, here mass of water is equal to this, sir.
Yeah, mass of water whose thermal capacity must be equal to the thermal capacity of the given object. That mass of water is called water equivalent.
Okay, sir, understood, sir.
Now, yeah, ask. One more girl is there. Ask. Ask them what the doubts. You can feel free to ask. Is it clear, guys?
Clear.
Yes.
Remaining peoples are there.
Yes, sir.
Next, Nandan, Kushal.
Yes, sir.
So, right, this is about water equivalent. You can copy this. Copy it. Is that completed, students?
Complete.
So, right. So, this is also very, very important. Heating curve. So, heating curve. First, ladder you can write result first. This is a beaker. It consists of solid ice. It consists of these are the ice rocks. Okay, ice rocks which are at some minus 80 degrees centigrade. And there is one thermometer is there. There is one thermometer which was fixed here to measure the temperature. Okay. It was a thermometer. No need to draw this diagram. Just to understand that I'm drawing this diagram. Okay. So this is the thermometer. And if this beaker was put it on a constant flame, okay, so constant flame means we are not increasing the amplitude of the flame. So just we are making this constant. So here the heat is given at constant rate. So think about a constant rate. For every equal interval of time, the temperature in the thermometer readings are taken down. Okay, for every say for every 2 minutes. Okay, so we are heating means what is going to be happening there. So just what will be happen means at first what will be happen, the temperature will be increases from -80 to 0 degrees centigrade. Then after that the complete ice will start melting. Once if the ice starts melting means what will be there? Water will be there. So those water temperature is raised from 0 to 100 degrees centigrade there. Then what will be happen again? The boiled water will be converted into steam. Steam only. So this is the process. Ask them. This is the process which was going on here. So from the instant ice to till the instant when the steam is formed, at a regular interval of time 2 minutes, the reading of the thermometer values are taken down with respect to the time. And if the graph is drawn between the temperature and time, so how the graph is appeared means this is the temperature T or theta, and this is nothing but time. Okay, time not T. So the graph is appeared to be like this. The graph is appeared to be like this. Okay, so this is the graph is appeared to be like this. So why this graph is appeared to be like this? From here to here, temperature is increased -80 to 0 degrees centigrade, and temperature remains constant for some time. Okay. Let us say T1 here, and let us say T2 here, and let us say this is T3, and this is T4. Once you can notice this, between 0 to T1, the temperature of the system has increased. Between T1 to T2, temperature remains constant. Between the interval T2 and T3, temperature is increases, and between T3 and T4, temperature is remains constant. So see here, guys, constantly we have supplied means from 0 to T1 at what rate we have supplied the heat to the system. At the same rate, we have supplied the heat between the interval T1 and T2. At the same rate between the interval T1 and T2. At the same rate between the interval T3 and T4. So here I have supplied the heat. Temperature is increases with respect to the time. If I supply the heat at constant rate also, here the temperature does not change this. So why this temperature does not change this here? Where it goes, the supplied heat is. Where it goes. So I have supplied the heat between 0 to T1, it is visible that the temperature is increasing. At the same rate, I have supplied the heat between the interval T1 and T2. Even though if I supplied heat at constant rate as like earlier, also I did not notice any rise in temperature here. The temperature was kept constant for some time. There onwards, temperature is increasing. So here, why temperature is constant? Where it goes, the heat which we have supplied means.
Latent heat diffusion.
Yeah, what?
Sir, the latent heat. Latent heat.
Regarding that only, to go through that latent heat, where it goes means the heat which I have supplied between the time interval T1 and T2, that was absorbed by the system, so that the system changes its state from solid to liquid. Solid to liquid. So here at this point, this is nothing but melting, I can write. So until the extent when the entire ice is melts, the ice temperature was kept at 0 degrees centigrade. There onwards, due to the supplied heat, the water temperature will increase from 0 to 100 degrees centigrade. Again here what is happening means, again here it is
boiling.
Until the water is completely turned into steam, the temperature of the system remains constant. So in the time interval T1 and T2, which we have supplied the heat, that heat is utilized to convert its state from solid to liquid. And between the time interval T3 and T4, whatever the heat which we have given to the system, that is used to convert its state from liquid to gas. Liquid to gas. So therefore, this process is known as melting, and this process is known as boiling. Okay. So therefore, here whatever the heat which we have given, that is known as latent heat. What is mean by latent heat means the amount of heat required, for unit mass of substance to change its state from one phase to another phase. Example, solid phase to liquid phase. Example, liquid phase to gaseous phase. That is known as latent heat. For example, latent heat of ice that is equals to 80 calorie. Latent heat of steam that is equals to 540 calorie. What it means by 80 calorie means 80 calorie per gram, 80 calorie per gram. So what it means that if 80 calorie of heat is supplied to 1 gram of ice at 0 degrees centigrade, it is turned into water at 0 degrees centigrade. To convert 1 gram of ice at 0 degrees centigrade to 1 gram of water at 0 degrees centigrade, we have to give an amount of heat is 80 calories. Okay. Similarly, to convert 1 gram of water at 100 degrees centigrade to 1 gram of steam at 100 degrees centigrade, we have to supply a heat of 540 calories. So, by absorbing the 540 calories by 1 gram of water, it is turned into steam. By absorbing this 80 calorie of heat, ice is turned into water. So this is about latent heat means. What is mean by latent heat? The heat required for unit mass of substance at constant temperature. The heat required for unit mass of substance to change its state from one phase to another phase. So either from liquid phase to solid phase to liquid phase, or liquid phase to gaseous phase. So to change the state of the system for unit mass, whatever the heat we need to give it to it, that is known as latent heat. Latent heat of fusion of ice is 80 calorie. Latent heat of vaporization of the steam is 540 calorie per gram. So here 80 calorie means what? If you supply 80 calorie of heat to 1 gram of ice at 0 degrees centigrade, by absorbing this 80 calorie of heat, the ice will be converted into water. There, the solid phase of matter gets converted into liquid phase. Similarly, 540 calorie of heat is supplied to the hot water, which is at 100 degrees centigrade. By absorbing this 540 calorie of heat, so liquid phase of matter gets converted into gaseous phase. So students, remember this. How heat is absorbed when solid is changes from changes to liquid, and the liquid changes to gas. In a similar manner, heat is evolved when gas is changed into liquid and liquid changed to solid. Okay. Heat is absorbed when solid converted into liquid and liquid converted into gas. Heat is given out when gas is converted into liquid and liquid is converted into solid. So that is about this. 80 calories absorbed to convert the ice into water, and 80 calorie has to be taken out to convert water into ice per 1 gram per 1 gram. So that is about the latent heat. So write this one. Write this one. Heating curve. So here it is. Solid plus liquid, both will be there. And here it is this is about heating curve. Students got it, heating curve? Clear on that? Is it clear, guys? Heating curve. You can ask any doubts are there.
Clear, sir.
Yeah. So write it fast. Okay, we need to complete the theory of calorimetry. Okay, so make a next latent heat. Next one is you can write the latent heat. So note down this latent heat. The amount of heat required. The amount of heat required for unit mass of substance. For unit mass of substance. For unit mass of substance to change its state. To change its state from one to another. To change its state from one to another at a constant temperature. To change its state from one to another at a constant temperature. At a constant temperature. Change its state from one to another at a constant temperature is known as latent heat. Is known as latent heat. Is known as latent heat. Next subheading. Okay, or else we can write so this one. So here, latent heat L is equals to dq by dm. Continue with that. Latent heat L equals to dq by dm. That implies L is equals to q by m also. So let by absorbing dq amount of the heat, dm amount of the mass as a change in its phase means latent heat L equals to dq by dm. Okay. So here, for example, simple one amount. So this is a dm amount of the mass is there. So here we have given dq amount of the heat. By absorbing this dq amount of the heat, here dm amount of the mass has changed its phase. Either it might be solid to liquid or liquid to solid means what is a latent heat? So for dm amount of the mass, we have or we need dq amount of the heat to change its state means so for unit mass, what is the heat required? dq by dm for unit mass heat required to change the state. That is known as latent heat. Latent heat L equals to dq by dm or L equal to q by m. SI unit will be, what is an SI unit of latent heat? Joule per kg is an SI unit of latent heat. It can also be in calorie per gram also or calorie per kg also. Okay, so it can also be. Next heat subheading, latent heat of fusion. Latent heat of fusion. Latent heat of fusion. So latent heat of fusion. Latent heat of fusion. Note it down on that. So the heat required. The heat required. The heat required for unit mass of substance. The heat required for unit mass of substance to change its state from solid to liquid. To change its state from solid to liquid. To change its state from solid to liquid. Next point, latent heat of fusion of ice is so then L ice that's equals to 80 calorie per gram. 80 calorie per gram. Latent heat of fusion of ice is 80 calorie per gram. Students, these are the standard values. We should remember that. If they have given in the problem is okay. Otherwise, we need to substitute these values. Sometimes they may not give this value. Sometimes they may give this value. That's why better to remember this one. Okay. Next one, next subheading. Latent heat of vaporization. Latent heat of vaporization. Latent heat of vaporization. Latent heat of vaporization. So then here what we can write, note down this is point. The amount of heat required per unit mass of substance per unit mass of substance to change its state from liquid phase to gaseous phase. Liquid phase to gaseous phase. Next point. The latent heat of vaporization of steam. Latent heat of vaporization of steam. Latent heat of vaporization of steam is equals to 540 calorie per gram. Latent heat of vaporization of steam, that's equal to 540 calorie per gram. I think you know the meaning of this. What is 540 calorie per gram means? 540 calories of heat required to convert 1 gram of water. 1 gram of water at 100 degrees centigrade to 1 gram of steam at 100 degrees centigrade. Similarly, from the steam, if you are extracted 540 calories of gram from 1 gram of steam, then that steam is converted into water like this. So that is about this latent heat. So next, keep separating the principle of calorimetry. The last theoretical topic on this one, principle of calorimetry. Okay. So listen. So that we can write to listen. So for example, I have here 2 beakers. This is the 2 beaker. So in this beaker, some liquids are there. Okay, so this is the liquid A of certain temperature, some 60 degrees, and this is the another beaker, which is of beaker B. This is also having some different liquids whose temperature is some 20 degrees. Okay. So now, if these 2 beakers of the liquids are poured into a third beaker, say C. So now we have these 2 liquids are mixed together and then poured into the beaker C. So then, what will be the temperature of the resultant liquid means definitely that temperature must be less than 60 degrees and must be greater than 20 degrees. And this is the common thing which we can notice in day-to-day life. Hot water and cold water both are added, that then we can get the resultant one of temperature which is less than hot water, and the temperature of the resultant water is more than cold water. The same thing here. So if these 2 liquids are at a different temperature are added together, then we will get the resultant is theta temperature. That theta must be less than this maximum value and greater than this maximum value. So then what is the principle of this calorimeter means? two substances are at different temperature are mixed together, then what will be happened? So heat will transfer from a substance at higher temperature to a substance at lower temperature until these two substances are acquire some common temperature. Till that instant, the heat will flow from hot body to cold body until both the bodies acquire common temperature. So it means that if there is no loss of heat to the surroundings, if there is no loss of heat to the surroundings, the heat lost by the hot body must be equal to the heat gained by the cold body. Whatever the heat which is lost here, so the same heat is transferred to this cold one, which is used to raise its temperature. This process is continuous until both the liquids acquire common temperature. So it means that what is the principle of calorimetry? So if there is no loss of heat to the surroundings, the heat lost by the hot body must be equal to the heat gained by the cold body. This is known as the principle of calorimetry. So that is about the principle of calorimetry means no down this. So understood, guys?
Yes, sir.
Understood.
Yeah. Other people also they can respond. No, why they didn't respond?
Yes, sir.
Okay. So right, note down this principle of calorimetry. When two different substances, when two different substances are two substances, when two substances are at different temperature, mixed together, mixed together, mixed together, mixed together, mixed together, then one of them loses heat, one of them loses heat, and other gains the heat, and other gains the heat till other gains the heat till both of them acquire common temperature. Both of them acquire common temperature. Okay. Next point. Both of them acquire common temperature. Next point. Next point. So, if there is no loss of heat, if there is no loss of heat, there is no loss of heat in the system. If there is no loss of heat in the system, heat lost by hot body or hot substances, anything we can keep, hot body is equals to heat gained by cold body. So this is called principle of calorimetry. Okay, don't write this is called principle of calorimetry. This is known as principle of calorimetry. So that is about the principle of calorimetry. Next, one more point is there. Note down this. Is it written on already? Heat lost by hot body equals to heat gained by cold body. Okay. So note down this. Let two substances M1 comma S1 comma theta 1 and M2 comma S2 comma theta 2 bracket you can write theta 2 is greater than theta 1. Let two substances of M1 comma S1 comma theta 1 and M2 comma S2 comma theta 2 are mixed together, mixed together, mixed together, mixed together, and theta is the resultant temperature, and theta is the resultant temperature, and theta is the resultant temperature, and theta is the resultant temperature. Then Then how can I calculate theta? Have a look on this. So here theta is the resultant temperature, means that theta must be less than theta 2 and that theta must be greater than theta 1. So among these two temperature, which is the greatest value theta 2, which is the least value theta 1? If I mix it together, then I should get the temperature which is less than this maximum value and greater than this least value. That's why I should get the resultant temperature somewhere in between this. Okay. So then how to calculate this theta means according to the principle of calorimetry, what can I write? So heat lost, that's equals to, I can write heat gain. So then which bodies loses the heat means this is the hot one, that's why this is loses the heat. Which bodies gains the heat means this is the first one, cold body, this gains the heat. Hence heat is lost by the second body and heat is gained by the first body according to principle of calorimetry. So then this is dq2 is equals to, I can write dq1. Already I got that dq, that's equals to what can I write? Ms into d theta only. Already we have derived that ms into d theta. So then what is dqt means mass and specific heat and temperature difference. What is mass here? M2, specific heat is S2. Temperature difference means initial temperature is theta 2, final temperature is theta, means here heat is lost, that's why the temperature difference is theta 2 minus theta. Even you can take theta minus theta 2 also, you can get negative. Negative sign indicates that heat is lost. Already I have considered heat is lost, that's why no need to consider the negative once again. That's why this is the heat lost. And what is the heat gain? Same formula, dq1 means product of mass and specific heat and temperature difference. So here mass is m1, specific heat is s1. Temperature difference means initially temperature is theta 1, it is raised to theta, means this is greater 1. That's why I can write theta minus theta 1. So it means that the next step, what can I write? M2 S2 theta 2 minus M2 S2 theta is equals to M1 S1 theta minus M1 S1 theta. So keep this theta terms on one side and remaining terms on one side. If this negative term is taken to this side, that will become plus. Already this is there. So therefore M2 S2 theta 2 plus M1 S1 theta 1, that's equals to M1 S1 theta. And if this negative term is taken to that RHS side, it will become plus M2 S2 of theta. So theta is common among these terms. Here I am writing. Are you able to see? So I think it's not visible there. So let us write here. So therefore here if I theta is taken out, then so theta of m1 s1 plus m2 s2 is equals to, we can write m1 s1 theta 1 plus m2 s2 theta 2. So therefore if this term is taken that side, it will come into denominator, then the resultant temperature theta equals to m1 s1 theta 1 plus m2 s2 theta 2 upon m1 s1 plus m2. So this is about the final temperature of the mixture. For example, three liquids means some of them. Three liquids are there then. Then here we got m1 s2
Theta
theta
3 by
m2 s2 theta 2 no? Plus m3 s3 theta 3 divided by plus m3 s3, we will get one more term. So like that, n number of liquids also we can use this formula. N number of substances also. So this is about the heat loss to heat gain and principle of calorimetry. So with this theoretically, the concept of calorimetry is completed. Numericals we will solve in the next class. Okay. So guys, is it clear? Please respond all.
Yes, sir.
clear, sir.
Yes, sir.
Is there any doubts you can ask?
Understood, sir.
Which one? Yeah. Okay. So right, is that clear? Have you written all?
Yes, sir.
Yes, sir. Written.
Yes, sir. Clear.
So right guys, see you on next class. Okay.
Thank you, sir.
Thank you,
Thank you,
sir.
sir. Bye, sir.
Yeah.
Thank
Right.
you, sir.
Bye to all. So your name? Abdul. Abdul. Understood this? Why this term is got it? So see on this.